So good afternoon, everyone. It's a great pleasure to be here. My name is Tommaso Macri. I'm the Executive Account Manager at QuEra Computing. So today I want to give you an update of our technology and commercial roadmap at the company. But before, let me start by saying a few words about QuEra. So QuEra is a quantum computing company that is based in Boston, Massachusetts. We are really at a bike ride from Harvard and MIT, which gives us, of course, the advantage of being very well connected with the quantum ecosystem, or one of the major academic quantum ecosystems in the world. The mission at our company is to build and productize quantum computers that are based on a specific technology, which is called neutral atoms. Since November 2022, we work with a major cloud provider to offer cloud service to our first generation quantum computer that is now used by several organizations among partners and customers to approach problems across different types of verticals in quantum simulation, combinatorial optimization, and machine learning. Over the past 3 years, so this is my third year at Quantum Korea, together with my colleague Min Ho, we've been engaging with the Korean quantum ecosystem quite a lot. We started about a couple of years ago with the signature of an MOU with KAIST and the city of Sejong. And the most recent engagement that we had was a 2-hour-long tutorial for the Korean quantum community to focus only on our neutral atom quantum computing technology. And of course, if you're interested in proposing any activity with us, feel free to reach out to us. We're really happy to engage with you. So this week, we are present at Quantum Korea and in many other, several other events. We will start tomorrow morning with an event, a tech forum in collaboration with the US Embassy, held here at the aTcenter. If any of you is interested in attending, we are currently overbooked, but we are really happy if there is any specific request to try to accommodate you as well. Then in the afternoon, I will be giving a couple of presentations at QuENSA to talk about standards in the quantum for quantum technologies, and then a presentation and a panel at Strong Korea Forum organized by the major financial newspaper here in the country. And I'm happy to have at the booth, B04, my colleague Ayumu, who is the country manager of QuEra Japan, can tell you a little bit more about our experience there in Japan. And I will say a few things towards the end. And my colleague Min Ho, who is the head of laser systems, that can dig a lot more into the technology and engineering of certain setups that we are developing. So let me tell you a few words about our technology, how neutral atom quantum computers actually work. There are several advantages associated to neutral atoms. Probably one of the major ones is that we are actually working with natural qubits. Natural qubits means that we are really using atoms that we take from nature. We use specific atomic species called rubidium-87. And differently from artificial qubits that kind of need to be calibrated individually, neutral atoms respond to external electromagnetic fields all in the same way. The second important feature is that the systems are intrinsically scalable. We can work with systems that have thousands or even tens of thousands of atoms without the need of complex interconnects. That is still in a relatively early stage in terms of technology development. There are some capabilities associated to quantum computing, for example, the possibility of long-range connectivity that make them particularly relevant for specific implementations of quantum algorithms, and in particular for certain applications in quantum error correction. Last but not least, these systems operate at room temperature, basically reducing the footprint and the engineering complexity of the devices. On top of that, the flexibility of the encoding of the information within the qubits or within the atoms allows us to map the qubit basis states in different ways with our rubidium atoms. In particular, we can essentially combine two complementary modalities to perform quantum computation within the same physical setup. If we choose, for example, two states, one belonging to the ground state manifold and one which is called the Rydberg state, which is a highly excited electronic state of rubidium, to create our qubit, we end up in developing essentially what is called the analog quantum computing mode that relies on very strong and fast operations thanks to the excitation to the Rydberg state. So the computation here works by preparing a register of qubits that here is denoted by a set of zeros, and then changing or designing laser pulses in order to change the dynamics, the microscopic dynamics of this multi-qubit system. On top of that, we can also play with the geometry of the system by creating square arrays or more articulated geometries, for example, these Kagome lattice. But we can also be even more creative, creating a map of the world where each one of the dots represents a single atom. Or by overlapping several pictures, we can write down the first hello world with an analog quantum computer. But this is not the only choice. We can also encode the qubit-based states or the 0 and 1s in a different way, essentially by coupling two internal states belonging to the ground state manifold to what are called hyperfine states, creating very long coherence times, and switching on and off the interactions to create two qubit or multi-qubit gates by coupling one of these two states into the Rydberg state. And so we can essentially, we can break down our algorithm into a set of native single qubit, two qubit, or multi-qubit gates, giving rise into essentially a circuit. All this technology has been combined by our scientists and engineers to create our flagship products, the first generation quantum computer that came online back in 2022, which is still, by the number of qubits, the largest quantum computer available on the public market. It has an uptime of 130 hours a week. We started with 10 hours 2 years ago, and now we are at more than 130 hours over the 168 hours that we have in a week. So a very large amount of time that this machine is available. And we develop a number of use cases, as I mentioned earlier, across several areas. In particular, our machine has been used as a result in several very relevant scientific publications, including this one that appeared a couple of weeks ago on the observation of string breaking in 2+1 Rydberg quantum simulator that was published in Nature. And if you're interested in knowing a little bit more about that, please stop by our booth. I'm really happy to talk about some technical details related to this work. The second generation machine is a gate-based machine, again with 256 qubits, that has been recently operated in our headquarters in Boston to do very powerful demonstrations of quantum error correction with logical qubits. In particular, we released this paper back in December related to the experimental demonstration of logical magic state distillation that in very simple words means essentially enabling for such a large system size the possibility of creating a full or a universal basis set for gates for applied to logical qubits, which was the first realization of its kind. Very importantly, this system has not only been used for scientific demonstrations, but it is now actually being installed in Japan at AIST, which is essentially 1 hour flight from Seoul, alongside the ABCIQ supercomputer. And I will show you a much nicer picture of this very same machine now installed at AIST. It is a machine that is very much thought for integration with HPCs, not only because of it's kind of complementary from the perspective of power consumption, which is much lower with respect to the standard supercomputing systems, but also because it kind of combines the classical and the quantum modality into a single device. So This is essentially the technology that we are developing at QuEra. How can we essentially enable our partners and customers to get value out of our technology? At QuEra, we believe there are three main pillars. The first one is, of course, by developing quantum systems and make them available either through the cloud or through some on-premise deployment. Deployment that comes also with dedicated support, not only to learn and use the technology, but also to build the ecosystem around itself. The second pillar is more focused on developing the cutting-edge research that we've been doing together with strategic academic collaborators to perform, for example, research around quantum error correction or hybrid algorithms that really exploit the combination of classical and quantum computers. The third area is where we like to focus the most with commercial customers, as well as with other strategic academic customers or academic partners, which is what we call application co-design. That is really focused on the so-called full stack optimization of application pipelines that combines the best of our quantum capabilities coming from the hardware with the optimization of the algorithm specificities that make those capabilities essentially shine for that specific application. And I want to be concrete and show you some examples. So all of this would not be possible without, of course, the help of our strategic partners. Last year, we created a partnership model that goes under the name of QuEra Quantum Alliance that by now counts with more than 20 partners. And we realize that there are many among these partners, there are quantum software companies, there are classical system integrators, there are firms that work more on the VC side, and all of them essentially enable different pieces of the quantum ecosystem that we at QuEra are currently building. In terms of applications, let me mention some very recent developments, some recent engagements with pharma companies such as Merck and Amgen. In collaboration with Deloitte, we developed algorithms inspired by quantum machine learning applications that will be applied to clinical trials. A different area where we explored weather forecasting applications together with Moody's, and back with Deloitte, smart manufacturing processes that could be optimized by the use of a certain quantum reservoir learning that we, again, developed internally at QuEra. Probably the area where we are currently focusing the most is actually the one of life sciences. We developed a very strong, very close collaboration with an organization called Wellcome Leap that is running a program called Q4Bio or Quantum for Bio to develop pipelines that are very relevant for life science applications. We have some strategic partners that include the University of Nottingham and Facecraft in the UK to study quantum algorithms to speed up drug design processes or protocols for myotonic dystrophy, as well as the study of the investigation of binding affinity for ligand and proteins led by Harvard, by our co-founder Misha Lukin, in collaboration with QuEra, MIT, and other partners. Within this effort, QuEra has been extremely successful. We were able to lead two projects up to the phase 3 of this Wellcome Leap program, and I would be extremely happy to understand whether there could be similar opportunities here in South Korea to engage in this very important, very relevant area. The last thing that I want to mention before closing is the strategic partnership that we have been developing with ICE, which is the equivalent of NIST in the US, in order to deploy our second generation quantum computer that you see here installed and in a much better shape than what we had until a few months ago at our headquarters in Boston. The idea here is not only to provide our customer, our partner, with the quantum computer, but really to be a critical part of the building of the quantum ecosystem that is envisioned in a strategic way by the Japanese government, that recently created the so-called GQuAD Center that basically aims at combining both classical supercomputing capabilities that are enabled by several hundreds of GPUs from NVIDIA, together with the quantum node that is provided by QuEra. So this is essentially a kind of industry first example of the integration of a neutral atom quantum computer with a classical counterpart. So with this, I would like to conclude my overview of the technological and the commercial achievements and status at QuEra Computing. I would be extremely happy to have you at our booth, B04, together with my colleagues, Ayumu and Minho. Thank you so much for your attention.